All right, now we just have a couple examples of working with these. Look at the diagram to the right. The first thing the question asks is, how is segment WY related to XZ? Notice XZ has two congruent segments being formed and a right angle with it. That means WY must be the what? Perpendicular bisector. Exactly. Segment WY is the perpendicular bisector of XZ. Now, think about what that implies. That automatically implies to me that these two segments should be congruent and that these two segments should be congruent. So all of a sudden I got these two giant isosceles triangles going to be formed. So how do we do that here? First things first, they want to know the length of segment XV. Well, XV is equal to VZ because it's a perpendicular bisector, so we know that one's 4. Not a lot of work you had to show on that one. What's the length of segment WZ? Well, WZ is equal to which one? WX. And since they give you a decimal, yes, you may give me a decimal. The length of segment XY. Well, it has to be the same as ZY. Not hard, as long as we mark up our diagram. So it's really simple, and I'm even going to put those on there so you can see it. Now, what kind of triangle, now here's the triangle we're looking for, is WXV? Well, the only thing, oh, by the way, this should probably be 3 marks just to make it fair. What type of triangle is that? Well, the only thing I know for sure is that it's the length of a hypotenuse is it's a right triangle. So we're going to say it's a right triangle. What do you guys think so far? Those are going to be the types of questions you're going to have in your quizzes and homework. It's not difficult, we just have to keep applying it. All right, let's look at the next one. It says use the figure to the right, which is for 6 through 10. Now, looking at this, right away, I see I have a segment that's being bisected and I have a right angle. So does that make IK the perpendicular bisector? So before you should think much about it, you should automatically be able to mark the two congruent segments. Remember, it's equidistant from the endpoints of the line segment. So first of all, they want you to find what x is. Well, to do that, that's going to be very easy. We're going to set them equal. 4x minus 3 equals 3x plus 2. So first thing we're going to do is subtract 3x from both sides. Add 3 to both sides. X equals 5. Now they want to know the length of segment HI. So what do we have to do? That's right, plug and chug, or plug it in, plug it in. So we have here 3 times 5 plus 2. What's that going to be? 17. Well, what's the length of segment JI? Well, it's the same as the length of segment HI. So I know there's 17. Let's look at number 9. L lies somewhere on segment KI. I don't know where it is. Here or here, somewhere on there. Then what do we know about its distance from H and J? It should be what? That's right, equidistant. You could say the same distance, equal distance, all those mean the same thing to me. Now, what type of triangle is the larger one? H, I, J. They're what? An isosceles triangle. So it's kind of cool how it works. Okay, let's get the last part here on this page. Last 2 theorems and something we need to know. It says, remember the distance between a point and a line is the length of the perpendicular segment from a point to the line. This says remember, but I don't think you guys really had that before. But let's think about how common sense this is. If I put a point up here above this line, so let's say point A over line L. What is the shortest distance going from the point to the line? That's right, you go straight down. Well, what type of angle is it if you go straight down? A right angle. Now, yes, there are other lines that you can draw, but they're not going to be as short as that one going down. So we're going to use the perpendicular segment's length to be the distance. Now, why are we going to use that? Because of our angle bisector. Look at the diagram down below. Notice when I have this angle right here, I need to be able to talk about distance being the same. So we're all drawing it the same way. We will always draw, and you can even flip it around here so it's straight down, the perpendicular segment. So it helps us keep it straight on this one. So that's kind of how we have to use that. So let's do the first theorem here. An angle bisector theorem says if a point is on the angle bisector, remember that means these two segments are the same, then it is equidistant, and in this case the perpendicular distance, think of it like that, from the sides of the angle. Which means these two segments now are automatically congruent to each other. How do we prove that? Angle, angle, side. It'd be angle, angle, and then your reflexive property for the side. So it's all using congruent triangles again. Now let's look at the converse, which means I flip-flop it. It says if a point is in the interior of an angle is equidistant. So I'm saying these two segments, and we get the right angles being formed, and that's point C we're talking about, from the sides of an angle, then it is on the bisector of the angle. Which means I automatically can assume the two angles are congruent. So we now just flip-flop it. So this diagram is going to be the key thing that we work with when it comes to the angle bisectors. All right, we're going to apply these two theorems on the other side.